Greetings, dear friends. I welcome you to TV Mathab. In today's lecture, we want to look at what we call Bayes' theorem. So, what is Bayes' theorem? We shall begin with the statement for Bayes' theorem, which statement says if we have E1, we have E2, we have E3 up to En. If we have E1, E2, E3 up to En, which are mutually disjoint events. If we have E1, E2 up to En, which are mutually disjoint events, with a probability of EI which is not equal to 0, provided I runs from 1, 2, 3 up to N. Then for any arbitrary event, for example, event A, which is a subset of a union of all elements from 1 to N of EI, where such that the probability of this arbitrary event A is greater than 0, then we shall have the probability of EI given A, which is same as probability of EI multiplied by the probability of A given EI, the whole of this one here divided by the summation of I, which is running from 1 up to N, of probability of EI times probability of A given EI, and our I will be running from 1 to up to N. So this is what we call the Bayes theorem. We are considering what we call mutually disjoint events, E1, E2 up to En, provided that the probability of EI is not equal to 0 for all the i's which run from 1 up to N. Then for any arbitrary event A, then we shall have this one true. So this is the statement, or what we need to prove as the Bayes theorem. So let us now come to the proof for the Bayes theorem, having looked at the statement for the Bayes theorem. Now let us come to the proof for the Bayes theorem. According to the statement, we have already seen that our arbitrary event A is a subset of the union of AIs which are running from 1 to N. So starting with that, let us now say since A is a subset of union of all AIs which are running from 1 to N, then we have A is same as having A intersection union running from 1 up to N of EI, but this one can be written as the union of I equaling to 1 up to N. Since this A is not affected by the EI, we can put the union outside by distributive property and write this one as A intersection EI. This one is only possible by what we call by distributive property or by distributive law. So we have this now. From there, we can still say that since A intersection EI is a subset of EI, A intersection EI is a subset of EI for I equaling to 1 to up to n. For I equaling to 1 up to n, these ones here are also mutually disjoint. They are also mutually disjoint events. Remember that we were considering here, we were considering EI, E2, E3 up to EN, which are mutually disjoint events. Now, using the same, since here we have that A intersection EI is a subset of EI, which EI are mutually disjoint events, then automatically it makes A intersection EIs also mutually disjoint events. So that's why we are able to consider this one here. So we are saying since A intersection EI is a subset of EI, for I equaling to 1 up to n are mutually disjoint events, then we have by additive theorem, we have by addition theorem of probability, we have by addition theorem of probability, we shall be having probability of A, which is same as probability of union from 1 to n of A intersection EI. This one here is actually same as from addition theorem. Then we can easily write this one as the summation from 1 up to n of probability of A intersection EI. So, which this one here can still be written as the summation of I equaling to 1 up to n. This probability of A intersection EI can still be written as probability of EI times the probability of A given EI. So this one here can be written as this. How? We know from compound theorem of probability, if I take you back by compound theorem of probability, we know that if you have probability of A intersection E is same as having probability of A times probability of E given A. You can still write this one as probability of E times the probability of A given E. So we have from compound probability theorem that the two are true. So it means if I have probability of A, which is same as the summation from 1 to n of probability of A intersection A of A intersection EI, then this one here, A intersection EI, I can use this one here to come up with this, such that where there is A intersection EI, this one here can be replaced with probability of EI times the probability of A intersection EI, if you try to relate it with what we call the compound theorem of probability. So that's why we are able to come to this one here. Now, so from here, we have the probability of A as that. So also by compound also by compound theorem, of probability, also by compound theorem of probability, we have we have we have probability of A intersection EI, same as the probability of A times probability of EI given A. I've already taken you through I've already taken you through compound theorem of probability, where we said that if you have probability of A intersection EI, you can write this one here as probability of A times probability of EI given A. Still, you can write the same probability as the probability of EI times the probability of A given EI. This is what we have by what we call compound theorem of probability. We have already seen that probability of A intersection EI can be written as probability of EI times probability of A given EI. We have considered this for that case, but we are also saying that from compound theorem of probability, we can still write probability of A intersection EI as probability of A times probability of EI given A. That is when we consider this one now. So using a compound theorem of probability, we are able to come up with this, and at the same time to come up with this. Now from this equation, which I'm calling a star star, I can also get the probability of EI given A by dividing through by probability of A, since probability of A is not equal to 0. Now for that case, let us make this one here the subject. So we shall have a probability of EI given A, same as the probability of A intersection EI divided by probability of A. Now we already know that this one here can be written as the probability of EI times the probability of A given EI. But we already have the probability of A. We already have the probability of A, that is from equation star. From equation star, we already have the probability of A. Now, we can again say probability of A, we have already seen that it is same as summation of I equaling to 1 up to n of the probability of EI times the probability of A given EI. And remember that our I runs from 1 to up to n. This one here is what we shall be calling the Bayes theorem. So that will be the proof. That will be the proof for Bayes theorem. So you can easily see that this one here is exactly the same that we had from our statement here. So this one here is exactly what we have proved, and that is the Bayes theorem. So with that, we are able to come up with the Bayes theorem. So basically, let us look at lastly at what we can call some of the important remarks. Some of the important remarks that we need to be considering when we are dealing with what we call the Bayes theorem. Let us look at some of the important remarks when we are looking at the Bayes theorem. The first one is about the probabilities P of E1, P of E2, P of E3 up to P of n. These probabilities here will be termed as priori probabilities because they exist before we gain any information from the experiment. So you recall that we were given these probabilities before, or we had these probabilities before the experiment, and after the experiment we were able to obtain some other probabilities. So the information about the events or the probabilities of the events before the experiment, or before we gain any information from the experiment, are what we shall be calling the priori probabilities. Then we also have the probabilities. For example, probability of A given EI, for which I runs from 1 to n. These probabilities here will be called likelihoods, because for them they indicate how likely the event A, which is under consideration, is able to occur for every given information about the probabilities that we have before. That is the priori probabilities. And lastly, we shall look at what we call the probabilities P of EI given A. So these are the ones that we obtain after the experiment is done. And these ones here will be called the posterior probabilities. This is because they are determined. This is because they are determined after the results. They are determined after the results of the experiment. They are determined after the results of the experiment are known. So when we are having the results of the experiment, then we are able to come up with the probabilities, that is of P of EI given A. And these probabilities here, we shall be calling them posterior probabilities. So we have got three kinds of probabilities. The first one was called priori probabilities. Then we have got the likelihoods, and we have got what we call the posterior, that is the posterior probability. So these are three different probabilities that we obtain if we have the information before or after we have obtained the results from the experiment. And this will mark what we call today's lecture about the Bayes theorem. So we shall be able to look at some of the different examples that where we can easily apply what we call the Bayes theorem. So in the next lecture, we shall be able to basically look at some of the examples, and we understand better on how we can apply what we call the Bayes theorem.